Hello, my name is Edward Cranford, and this is a pre-recorded presentation for the 2022 International Conference on Cognitive Modeling, for which I'll be presenting my research on combining machine learning and cognitive models for adaptive phishing training. Our research explores methods for personalizing anti-phishing training. Organizations typically use simulation campaigns for anti-phishing training in which employees are selected randomly to be sent a simulated phishing email. If they fall for the attack, they are given immediate feedback and training to detect phishing emails. While more effective than no intervention, the method is non-personalized, while humans are adaptive and learn from experience at different rates. Personalized training requires a representation of the cognitive states of each individual in the organization. In our model of phishing susceptibility, we propose that phishing classification decisions are similar to other kinds of decisions from experience, in accordance with instance-based learning theory. For a given email, classification decisions are retrieved from memory by generalizing across similar past experiences. Decisions are therefore influenced by memory processes that contribute to learning and adaptivity, and are thus susceptible to biases. To personalize training, the problem is effectively one of scheduling. Individuals require different amounts of training, and the timing of interventions is important. Therefore, the question is who to target at each time step, and how can we strategically schedule interventions. Our proposed solution is to combine cognitive modeling with machine learning methods, and to frame the problem as a restless multi-armed bandit. The employees, or arms, are modeled as a Markov decision process, and we use a cognitive model of phishing susceptibility to estimate the transition probabilities for the MDP. The RMAP then learns the schedule of selection across the time horizon. We compare the RMAP solution to two purely cognitive solutions that use cognitive twins to inform which users to select at each time step. A simulation study that uses the cognitive model as simulated participants is deployed to compare the effectiveness of various selection algorithms, including a no intervention condition and a random selection condition. Our simulation task runs 1,000 users simultaneously across 100 trials. On each trial, users are presented a phishing email if selected for intervention, or a ham email if not selected. There are many factors that contribute to individual differences in phishing detection, such as demographics and personality factors, but two important ones that we focus on in the present research are overall email usage and phishing and network experience. These factors map well to the instance-based learning theory of decisions from experience. Each model agent is therefore initialized with a set of emails to represent individual differences in prior experience. We manipulated the number of emails to represent email usage and the proportion of ham emails to represent phishing and network security experience. These factors contribute to individual differences in propensity to classify phishing emails correctly. A k-means cluster analysis was performed to generate clusters of similar users, resulting in 4 groups that were high or low on either dimension. Our cognitive model of phishing susceptibility was built in the ACT-R cognitive architecture, and decisions are made in accordance with instance-based learning theory. This model was used as simulated participants in our simulation studies to generate transition probabilities for the MDP of the RMAP, and also for evaluating the selection algorithms. When presented an email, the model makes classifications by generalizing across past experiences in memory using ACT-R's blending retrieval mechanism. Decisions are thus influenced by recency and frequency of past instances, as well as their featural similarity of the current email to past emails. The features of the email include the sender, the subject, body, the linked text, and the underlying link URL. Similarities between features are computed using the UMBC semantic similarity tool, which generates semantic similarity values between two texts. This automates the process. This model has been shown in previous research to generalize across different task designs that use different databases of emails. In our formulation of the restless multi-armed bandit, the learner selects a user, or arm, for intervention and receives feedback, or a reward, based on the user's state. The goal is to maximize the total reward observed by the learner. We enforce a maximum budget of 20% so that we do not bombard users with intervention at each time step. Each user is modeled as a Markov decision process, which includes 2 possible states. Good, meaning the user always classifies emails correctly, and bad, meaning they always classify emails incorrectly. The possible actions include sending a phishing email for intervention or a ham email for no intervention. The rewards are either 1 for being in a good state or 0 in a bad state. The transition probabilities define the likelihood to transition from one state to another given the current state and action. We use the cognitive model to estimate these transition probabilities. Since we do not have human data to train an MDP, we use the cognitive model to simulate data. The cognitive model can make a priori predictions based on constrained mechanisms resulting from a theory of cognition, and our cognitive model produces purely generative behavior. Therefore, we simulated 1,000 cognitive agents performing the task paired against a random selection algorithm. On each trial, the agent is in a good state if their classification is correct, or a bad state if incorrect. Based on the sequence of decisions, we calculated the proportion of transitions from a good state or bad state at time t to a good state at t plus 1, depending on the action at time t, resulting in the transition probability matrix below. We note that this definition of transition probabilities means the reward function is sensitive to what types of emails users receive and their propensity for correct classification. This will be apparent in the results, and at the end of the presentation I will discuss current research that addresses this issue. To solve the RMAP, we used a superarm WCL to reduce the complexity and computational costs of learning the parameters for each user. Superarm means the users are clustered into groups, as was described earlier, and their learning experiences are combined. WCL stands for Whittle Index Q-Learning. Based on Q-Learning, the Q-star value captures the quality of taking action A from state S, and users are selected with the greatest Whittle index, which is defined as the difference between Q-star values for sending a phishing email, action 1, and a ham email, action 2. At trial 1, users are randomly assigned to states with 50% probability. Given the selection of users by the RMAP and the transition probabilities, users quickly transition toward good states. We see that performance then plateaus for no action and random conditions. This stabilization occurs as users match the transition probabilities. The transition probabilities are higher for no intervention due to the frequency of ham emails, and since the no action condition receives only ham emails, it settles higher than random. Most importantly, the strategic selection of users under the RMAP results in better performance than random and continues to improve across trials and outperforming no action. We designed two purely cognitive approaches that use a cognitive twin to personalize selection. The cognitive twin uses model tracing methods to track a user's history of decisions and uses the blending equation to compute the probabilities of classifying a future email as ham or phishing. The CogLow method computes the probability of classifying any email as phishing based on past decisions and sends a phishing intervention to those users with the lowest probabilities. The goal is to increase the future probability of classing a phishing email correctly for these users, always trying to improve the bottom of the barrel. CogAV uses a more complex approach that weighs the anticipated future benefits of a phishing intervention in terms of correctly classifying phishing emails against the anticipated future costs in terms of incorrectly classifying ham emails. We first compute the probabilities of classifying a phishing email as phishing or a ham email as ham, and then we add another phishing email to the history and compute the anticipated future probability of classifying a phishing email or ham email correctly. The goal is to send phishing emails to users with the greatest expected benefit of intervention while minimizing the negative impact on ham classification. To evaluate the effectiveness of the selection algorithms, we deployed a simulation study whereby the cognitive model was used to simulate 1,000 users performing the training task against each selection algorithm. The cognitive agents received the same initialization for each simulation. Multiple agents were run in parallel on each trial, and the selection algorithm determined which users to send phishing interventions. The RMAP was pre-computed, but all other algorithms were computed on the fly in real time. Each agent makes a decision before moving to the next trial. We compared 5 selection algorithms: no action, random, the RMAP, CogLow, and CogEV. We first examined the moving average accuracy across trials. The window size was set to 50. In terms of overall accuracy, the RMAP and CogEV perform similarly, while the random and CogLow perform worse. The no action results in high accuracy, but it only measures performance on ham emails and does not adequately represent overall user performance. When we examine the accuracy for ham and phishing emails separately, the results show that the random and CogLow algorithms increase phishing accuracy, but at the expense of ham accuracy, worse so for CogLow. Meanwhile, the RMAP shows little loss in ham accuracy, but only modest improvements in phishing accuracy. The CogEV algorithm, on the other hand, shows little loss in ham accuracy, but substantial improvement in phishing accuracy. Overall, these results indicate that CogEV is best at improving phishing detection, but these results are biased by the selection of users. For example, the no action condition shows high accuracy because no users are selected for intervention. Other conditions may be misrepresented as well depending on which users are selected for intervention. Therefore, we examine the selection preferences of the algorithms. In the figure on the top right, we plot individual user accuracy for ham and phishing emails as a function of the proportion of phishing emails sent to them. The heat map shows that users that receive fewer phishing emails on average are colored blue, and users that receive more phishing emails on average are colored yellow to red. The results show that the selection algorithms display vastly different patterns of selection across users. For the random algorithm, users that are sent more phishing emails perform better at classifying phishing emails, and users who are sent more ham emails are better at classifying ham emails. The RMAP displays a similar pattern as random, but more participants that are not given phishing emails perform very poor at classifying phishing emails. For the CogLow algorithm, users cluster toward the top right, pushing the top left tail seen in the random to the right. And those that are given more phishing emails also do well at classifying ham emails. But those that are given fewer phishing emails still perform poorly at classifying ham emails. Meanwhile, the CogEV sends some users many phishing emails, but they perform very poorly at classifying ham emails. When we look at the distribution of selection by clusters, the random algorithm is of course distributed quite equally. The RMAP, however, tends to select users with high init length and low ham proportion, which are incidentally those users that are already good at classifying phishing emails. The CogLow algorithm tends to select users with higher init length and higher ham proportion, which are those that are most in need of intervention due to greater email usage and least phishing experience. Finally, the CogEV algorithm tends to spread selection more evenly, but does display slight preference for users that have low init length, or those with low email usage and those in which intervention will be most impactful. Finally, we examined signal detection measures because they provide an unbiased measure of performance compared to overall accuracy. We use a log linear adjustment to account for missing cells, so the minimum hit rate, or true positive rate, and false alarm rate, or false positive rate, is always 0.5. The ROC curves in the top right show that the hit rate for correctly classifying phishing emails is better given any intervention than no intervention. However, there is not much difference in hit rates and false alarm rates for any intervening selection algorithms compared to the random algorithm, and in the high-high and low-high groups, hit rates for the RMAP are lower compared to other algorithms. We also examined the change in D' from the first 20 trials of training to the last 20 trials of training to get a sense of the improvement in phishing detection given training. The random intervention only improved users with high ham proportion, or those with little phishing experience. The RMAP showed large performance decrease for the low-low group and only improved the high-high group, who were sent the fewest phishing interventions. However, based on the ROC curves, this improvement is likely due to improvements in ham classification. The CogLow improved performance in all groups except the low-low group, and the pattern followed the same as that for selection, improving more as the number of phishing emails presented increased. The CogEV is the only algorithm to improve performance across all clusters. The current research is a first step at combining cognitive models with multi-armed bandits to personalize phishing detection training. The RMAP showed potential, but also revealed potential shortcomings, highlighting the need for improvement. Firstly, the reward function and/or definition of transition probabilities needs reformulation so that it learns to select users most in need of intervention instead of those already doing well. We are currently exploring ways to redefine the transition probabilities. One method is to define states solely on phishing classification accuracy. Initial results are promising and show that the method does indeed select those users most in need of phishing intervention. However, it is overly focused on improving phishing accuracy at the expense of ham accuracy. Another method is to increase the number of states. More fine-grained states would allow for better representation of users and thus better selection. Another limitation of the current research is the design of the training task. It is difficult to interpret the signal detection measures because of differences in how many phishing emails individual users are presented. Therefore, it would be better to give explicit testing phases before and after the training phase in order to accurately assess performance changes given training. Overall, the CogEV algorithm proved most successful at increasing phishing detection accuracy while minimizing false alarms. Cognitive solutions have lower computational overhead and the advantage of selecting users at the individual level. It is likely, however, that the RMAP would fare better as the number of clusters increases. Therefore, we plan to explore the optimal trade-off in number of clusters and computational cost. Future research is aimed at refining the RMAP formulation, as discussed earlier. We also plan to explore methods of further combining the pros of both cognitive models and the RMAP. For example, the cognitive model could be used to update transition probabilities over time, or to provide additional learning rate estimations in place of Q-learning. Finally, we aim to validate the simulation results in human behavioral experiments while exploring methods to further personalize training by not only selecting which users to target, but which phishing emails to send them. Thank you very much for listening, and if you have any questions, please feel free to contact me at the email address below.